Okay, so now we come to our write-up. Very important part of this course, because what we want to do is we want to calculate numbers, we want to do the statistics, but then we want to publish this in a way that others who may not have as much experience as we do can still understand. And so I've got this page out there for you to look at. We're going to write up the results of our regression analysis. We were looking to see if we could predict the album sales um, by looking at the advertising budget and even by manipulating the advertising budget. And so we might say something, the purpose of the analysis is to determine if advertising budget affects album sales. And you can imagine this would be really valuable. We can use this in the schools. Does our school budget affect test scores? Okay, so the independent variable is the one we can change directly. I should add the word here, directly. We can always pour more money into that advertising budget. And then we hope by influencing the independent variable that the dependent variable will also change. This is the one that we want to measure and the one that we want to grow, right? In the end, this company wants album sales to go up. It's good for everyone. And so if one of the things that helps those album sales go up is advertising budget, then that's what they want. So we made our scatter plot to see if the data looked reasonable. And you could write about this a little bit. You could tell us that there weren't any extreme outliers. That would be a point that's off the graph here, except that, of course, the graph would have to move. But if all of our dots were right here and then we had one dot way over here, it would say there's something wrong with that measurement. It's such an outlier. We don't have outliers. We have some points like this one right up here. So here is a really high amount of album sales without much advertising. So this one and this one and this one, they are not maybe as close to that line of best fit, but you can imagine that maybe there were other forms of advertising going on that also had an effect on album sales. In general, I'd say the data looks reasonable. We want it to look kind of like a cloud, maybe with some kind of a progression here. Like you can see, yeah, this is a cloud, but our eye does kind of want to be drawn up. And sure enough, the line of best fit goes up. So yeah, we'll say that this data looks reasonable for regression. We can also say regression is a robust procedure. And robust means that we can still learn a lot statistically and predictively when we conduct regression, even if all these dots aren't exactly on the line. That's okay. We have a great procedure here that will work for us. So what's our null hypothesis? Remember, the null hypothesis is that nothing's going on. So the null hypothesis is that budget does not affect sales. So I can pour as much money as I want into that budget, the sales aren't going to move. My alternative hypothesis is, and I'm going to make this what we would call a one-tailed hypothesis, like I want to predict that as budget increases, sales increase. If it was a two-tailed hypothesis, if I didn't know, so two-tailed means I can't specify the direction, non-directional. I'd say, well, the more money I pour into the budget, I'll see some kind of change. Either the sales will go down or the sales will go up. Something will happen, but I'm not sure which. And of course, in this case, that's kind of silly. We know the sales should increase if we put more money into advertising. But in another instance, we may say, well, if we increase the percentage of fat in the diet, should that help the person gain weight or lose weight. We're not sure. Fat may help this person stay full longer and actually help them lose weight. So we would say there will be a change, but we don't know which direction it will go, and that's okay. Now, in education, we almost always choose an alpha level of 0.05, and that means that when we collect our data, and we compare it to our null hypothesis. Our null hypothesis saying there's just nothing going on. The line through this histogram is basically flat. I'm sorry, through the scatter plot. The line through the scatter plot is basically flat. Nothing's going on. We can pour a lot more money in and the sales stay about the same. Well, if we have this alternate hypothesis, how sure do we have to be of it? And what we say is this alpha level gives us the chance or the probability that maybe there was something going on and we just missed it. And we always have to have some sort of probability. In statistics, we just can't be 100% sure. And we've resigned ourselves to that. We say, okay, because we're collecting data from this sample, and it may not have been the best sample, or maybe our collection methods weren't perfect, or maybe our participants weren't perfect. I mean, album sales and advertising budget, both of those can vary for other reasons besides just the dollars and just the number of albums. So we give ourselves this little 5% window that maybe we missed something, but 95% of the time we found what we were looking for. When we say, yeah, I'm going to reject the null hypothesis, 95% of the time we're going to be right. And SPSS is pretty amazing. They actually use probability to come up with that statistic and to let us know, based on the sample we collected and the numbers that they see, what's the probability that we can reject that null, that the probability that we're seeing something different, that there is some kind of an effect. And so we almost always say 0.05. Now, if we're doing research where the end result is so crucial that we absolutely have to reject the null if there's any possibility, we might say 0.01. Like, it is so important to reject that null. Maybe the null hypothesis is you don't have cancer. And we want to make sure that you don't, and so we move that probability and make it very, very small. Or on the other hand, maybe we're not that, we'd much rather not reject the null if there's any chance that it could be happening, and the null is we don't need to move these people out of this neighborhood, something that, you know, if we reject it, it's going to cause a lot of pain for people. Then we might move it up to 0.2 or 0.3 because we don't want to put ourselves in a position where the type of error we make causes harm. In general, in education, we keep it at 0.05 because we do make decisions. They're not every so often right. 5 times out of 100, they might be wrong, but they're almost never life and death decisions, not like medicine or engineering where we're building a bridge. They're important. I'm not trying to say they're not important, but 0.05 gives us a good balancing place where we're 95% of the time we get it right. And in order to push ourselves to getting it right 99% of the time, we'd almost always come up with something that we couldn't reject, or that we couldn't say what we needed to say about it. So there's a trade-off here. So trust me on this one. We will talk about this in class and together on why we go with 0.05 generally. And so now we've come to our conclusions, and we're actually, what I didn't do before was I didn't write in here the p-values which go with that alpha. And I don't know if you remember, but in the output, it actually had a 0.000. So what I want to do is write that P is less than 0.0005. And the reason is we can never say the probability is 0. That's one of the things we've agreed upon as statisticians, that there's always a possibility as scientists. Like, we study, we come up with theorems, we prove those theorems, we do the best we can, but every so often we realize there's even more to learn. There's even more to learn about physics. There's even more to learn about chemistry. And it's changed so much since the day that I minored in chemistry in college, and it will continue to change even more. And so we leave open the probability just a little bit. It's not 0. It's less than 0.0005, so it's pretty low, but it's not 0. Okay, so both of these were less than 0.0005 because basically SPSS rounded it to 3 decimals, and in order to round something down to 0.000, it has to be less than 0.0005. Okay, so I have reported here the r squared, which is, let me just make sure I get out of this little, r squared is 0.335, whoops, 5. And this means that advertising budget can predict, and we could say, let's say 34%, let's round up 0.335 to 34, can present 34% of the variation in sales. Okay, so that means I still have 66% I need to figure out. There are other things obviously affecting sales, and that's why Field on his spreadsheet, he also recorded playing time and how good looking the band was. But at least 34% of sales seem to be related to this advertising budget, and that's a pretty big deal. That's a good argument for advertising. And so then here I have my statistical proof. I have an F statistic, and this F statistic is what we will always use in ANOVA. Interestingly, in regression, we can use the T statistic, and we don't use a T statistic in ANOVA. So you'll notice when we do t-tests, we'll use the T statistic. When we do ANOVA, we'll use the F statistic. And yes, it's crazy. It's crazy that there are 2 different statistics. But if you like this kind of thing, pull out your calculator, take this T statistic, 9.98, and square it. And guess what 9.98 squared is? It's 99.59. So actually, the T statistic and the F statistic are telling us exactly the same thing. And we'll talk later about why you would use one in one case and you would use another in another case. For this, though, it's better not to report both. I would go ahead and do the T statistic, and you can actually even delete the F statistic. I don't mind if you send me the F statistic, but in a journal article for regression, what we're really interested in is this beta right here in this sales equation, because this is what is telling us, it's demonstrating the predictive power of advertising. Now what your client can do is type in the number of advertising dollars they'd like to spend. Okay, 100,000 pounds. That gets multiplied by 0.578 and added to 134, and that gives your client a prediction for the average sales. What it actually does is it comes up with the number right on this line. Now, their first time, they may actually be more up above the line. The next time, they might actually be below the line. But on average, they should be hitting right here on that prediction line with that number of sales. And that's pretty powerful. That's pretty amazing that we can do that with this simple regression. We can tell you how much of the variability is accounted for by sales, and we can actually predict for you what your sales will be given what advertising budget you come up with. So we also can say from this equation, for every 1,000 pounds of advertising, notice I'm going back to the story behind my spreadsheet. So I'm going back to field's description. There's 1,000 pounds of advertising. I can say the sales will increase by, and now sales were also in thousands, so I can say 0.578 times 1,000, or 578 albums. And so now I can tell you, okay, for every 1,000 pounds you put into that budget, you'll have 578 more albums sold. And usually what we would do is we would say for every one, but then here it's times 1,000 because Field says the advertising budget is thousands, but really it's for every 1 unit increase in X, we predict a, and then this is the beta, 0.578 unit increase in Y. And that's kind of what we're saying here with our final write-up. 1,000 pounds of advertising mean you'll have an increase of 578 albums. Think about how you might write that up yourself. I'm not going to ask you to send me a write-up unless you'd like to. It's a pretty powerful technique, and it's very directly related to ANOVA. So I wanted to just expose you to it briefly before we dive deeply into ANOVA. Have fun with regression. If you have a little extra time, you might try to do regression and see if, well, I'd love to know, does the good-looking status of the band have anything to do with album sales? Can you predict album sales by how good-looking the band is? How fun. Okay, well, have fun with this, and thanks for sharing it with me.